Okay, let's get started. Today, we're very pleased to have Dr. Anya Portyankina from UC Boulder, from Laboratory for Atmospheric and Space Physics. Anya got her master's degree in physics and astronomy at Kharkiv National University in Ukraine, and then she moved on to Göttingen University in Germany to receive her PhD in astrophysics. And her main research is on remote sensing of planetary surfaces and atmospheres. And in particular, she studies the behavior of different ices and their interactions with atmospheres as well as surfaces to reveal how they are able to shape planetary surfaces into terrains we observe. So without further ado, please take it away.
Hi, thanks for inviting me. This is unusual for me and, well, interesting experience. Let's try doing that. So I'll be talking about Martian ices, dust, and winds. So these three are the components of all Martian climate, what's happening now at this time currently on Martian surface and near surface, so in lowest atmosphere. I want to acknowledge, of course, that the work that I'm showing is not only my own. There is a set of people who helped me out. Their names are listed in here. Quite international participation in that because, yeah, we are collaborating across the Atlantic as well about these topics. So if you don't recall anything else, this is a takeaway message that I want you to remember after this talk. So Mars is not a dead planet. It's an active world with exotic spring processes that shape its surface today in front of our eyes. We actually observe the changes, and I will show you some of those. And the whole idea of studying Mars is, of course, the biggest curiosity, scientific curiosity, but also understanding today's climate will allow us at some time to unravel the climate and geological records that is stored in Martian surface and subsurface right now, so we can learn what happened to this planet in the past. So these two main takeaway messages that I would like you to remember from today. And sidestep, the Mars is the closest right now to Earth. That happens about every 2 years. This one is especially close. So if you have an opportunity, go outside in the evening and look up. Here is an image, relatively recent one. And what you can see nicely here, this is taken, of course, from Earth with ground-based telescope. And you can see this 1,000 bright spot. This is southern hemisphere of Mars, and this is actually residual polar cap. We will be talking about polar caps a lot in this presentation. So this is a place to basically look at, we concentrate. Right now, Mars is in northern winter, southern summer season. So the seasonal polar cap that usually extends higher from the pole to the mid latitudes is currently gone so there is now no ice around here, and only the residual cap is left. So this is an interesting side point. Couple of things that I will be freely throwing around during my talk, and maybe some people who are not very familiar with Mars don't know. First of them is all the images that I use, I think all of them really are from high resolution camera that is on board of Mars Reconnaissance Orbiter, currently on the orbit of Mars. So it's called HiRISE for short. And you can see here its image is a really huge telescope that is mounted on the spacecraft. Is the highest resolution camera in the outer space. And here is an example of what it can do. This is the picture of Phoenix lander during its descent. So we captured the image while the spacecraft was going down through the atmosphere, and you can see the background, the huge crater here that Phoenix landed in. And if you zoom at this spacecraft itself, you even can see the straps from parachute to the landing module that the spacecraft is hanging on. So that's kind of resolution we are working with. This is the highest that you can get. Another little thing that you need to know is about Martian seasons. I will again be talking about spring mostly, but spring, summer, fall, winter. Same story as on Earth. Same story as on Earth. It's opposite in southern and northern hemispheres. On the very left here, you can see the different images of northern hemisphere of Mars that shows the decay of the seasonal polar cap. So in winter, in the winter hemisphere, CO2 ice condenses on the surface. Mars is that cold that it does not condense only water like on Earth, but also its main atmospheric component, which is CO2 ice. So it covers significant portion of the northern hemisphere. And then when spring progresses, it shrinks. So in here, the CO2 ice has sublimed and went back into the atmosphere. And here is almost all surface CO2 ice has sublimed. So there is all these variations Mars goes every year through. The opposite hemisphere does the same, just in the opposite time. We can see those changes when we measure surface pressure on Mars. So here is an example from Viking landers 1 and 2. They were at slightly different latitudes on Mars, so the absolute values are slightly different, and you see this shift. But you see this variation, which accounts for about 25% of surface pressure. Here is time on Mars during seasons, and I come to that in a second. And here is surface pressure, so you can see how much it changes through the year. And that's due to that effect that we saw on the right figure here, that CO2 basically from atmosphere deposits directly on the surface. What is this LSABS here? That's how we basically count time on Mars to make it easier. And this graph on the right should explain you that. So it's counted in degrees. Basically, it's position of Mars on its orbit in degrees around. So this 0, 30, 60, 90, so on. That's the LSABS. And it goes from 0 to 360. At LSABS equals 0 is northern spring equinox, so when spring starts in northern hemisphere, and 180 is the opposite, southern spring equinox. I will be talking a lot about time between 170 and about 270, so it's spring and southern hemisphere covering that. Martian sol is 1 Martian day. It's almost same as Earth day, but Martian year, it's almost twice longer than Earth's year. So while Earth does 1 orbit, Mars only does half. And that all, if you do the math, 1 degree in LSABS is approximately 2 Martian days or 2 sols. So those are a couple of basic things that will be important for the talk. And from now, let's see what actually it is about. Here I'm showing the morphological features associated with CO2 ice. So you can see a lot of different things. Again, all the images here are from high-rise camera. So you can see the scale bars, basically in all of them, that shows you how small features we are talking about. What I wanted to show on this slide is the diversity of features associated with CO2 ice. All of these fans are products of eruptions of CO2 jets, main topic of this talk, and they are basically surface deposits of those jets. Same about this very top left image here. In slightly different configuration over the Barhan dunes, you see those nice shapes with steep slopes where material runs down. But at this time, when this image was taken, this area was covered by CO2 ice layer. So it is in high latitudes of Mars, and it gets covered by ice in fall and winter. And in spring, when they start to defrost, such strange features happen there. So this kind of active processes also leave their marks on the surface. And in the bottom are some examples where we actually detected changes. So for example, here in the middle is similar to these dunes, but images taken when they are ice-free. And you can see that from one year, which is top image here, to another one, there are more of these slumps down with the alcoves that are being created on the crest of these dunes. In the bottom left image here, you can see that this gully, the very narrow one, after 1 year extended quite a bit. That's also one of actions of CO2 ice, where we think that material of CO2 actually ran down, and these two are two seasonal images, and the result of that is how those gullies are actually getting longer extent and being created to start from. A little bit less obvious changes in this image here, but still you can see that this area kind of different with one Martian year in between them. So I'll be talking mostly about these jets that are shown on top here in the colorful images. And for that, I also want to show you a little animation that we made of multiple high-rise images taken in the same season, so one spring. So you can see how much this area changes, how active and dynamic this stuff is. So you can see all these dark spots popping up and coming through. And you also, like here, you can see that it slowly sublimes the ice. The bluish bright side surface is always something related to ice. I repeat it once again. For your viewing pleasure, you can see the dark spots here popping up all over. Those are the fans that I was showing you zoomed in more in the previous one. You see how they change location, distribute more on this side. And here is when the surface starts to become ice-free and dark and come back to original image. So what are those? How are they created? Martian polar jets are direct result of what we called solid-state greenhouse effect. The idea is that in fall, in the surface of Mars, CO2 gets deposited, and it can be up to 1 meter thick layer. Oops, sorry about that. And CO2 has a special properties. It's transparent, invisible, and it's highly opaque in infrared. That means that it can act similarly to our atmosphere, where visible light can get through down to the surface, heat up the surface, but then it cannot escape because its atmosphere is opaque to infrared. So it creates the warming up effect. Same thing here happening when there is some sunlight and sun gets on top of the ice. It actually gets not absorbed, not on the top, but goes through and gets absorbed mostly in underlying layer. And it hits the surface underneath. But then this heat cannot escape. What happens is that heat starts to be turned into sublimation of CO2 layer from below. And then the pressure underneath starts to grow because you're turning ice into gas in basically same volume. Well, there is a little bit of volume coming from compression and sinking through the soil underneath the ice here, but still the pressures are quite high. So at some point the ice cannot sustain it anymore. The ice layer breaks and it creates the jet, which is shown here on the right with the artistic impression how this jet would look like if we could ever land there and see it. So I want to show you some of images taken with microscope of the CO2 ice. This is from experiments that we did in Aarhus University, and we try to figure out what is the form of ice and how it gets deposited in Martian polar regions. So we bring the chamber to the pressure and temperatures similar to what we get on Mars. Of course, we are never perfect, but yeah, that we try our best. And we see a lot of different kind of crystalline structures or CO2 ice forms that are quite weird at times. So for example, this ones I'm showing here is not fully understood why at some of our experimental runs we got this kind of shapes. But we also noticed that close to Martian conditions, we actually get something like this. So what I was talking about, it's kind of transparent in visible light. You can see this marking, dark and bright parts of our substrate where CO2 was deposited, and you still can see it through relatively thick layer. This layer is about 2 centimeters thick of the ice. So this is reminiscence of the very transparent water ice on Earth that you get when the very clean water in lakes freezes. Like if you ever seen Baikal Lake images, that's what happens. So that's the transparent form of ice. So that's the ice that we think makes this layer of CO2. So this jets, as you can see here, they are painted dark, and that's because when the gas rushes out from underground here and through the vent, it erodes some of the material here from below, and it brings it up into the atmosphere and then deposits on top of the ice. So this deposits is what we see as those fans that I was showing before. But by doing that, the CO2 gas actually does quite some erosion down here. And we do see the results of that in what we call RNI forms on Mars, or colloquially spiders. So these dendritic features that are like rivers on Earth, but they kind of go towards one center instead of following the gravity as rivers do. These are spiders on Mars. Here is a little bit more outlined, colorful image of this specific RNI form, where we try to analyze it morphologically. So you can see the different levels of channels coming from outside to inside. They are centrally symmetric, we think, because it started from one vent where CO2 was basically getting out somewhere around here, but with time it developed further and further. So the erosion spread from center to outskirts and created this feature. We do see them forming in current climate, not all of them. So actually the oldest, the more developed ones are mostly not showing any new developments, probably because we still having very short timeline of observations. We're only observing in high detail Martian surface for last, what is it now, 15 years? So about 7 Martian years of constant observations exist, and probably the changes of those huge structures are just below our radar still. But we do see the small ones popping up, the new ones, and here is an example where we actually detected appearance of new spiders over 4 Martian years and how it's developed. Interesting detail that this specific location is near a dune field, so we think that erosive force from sand that kind of stripped from the dune fields and was lying here is helping out, and then erosion is more active in this specific area. So we can have a pleasure to observe how the spiders start and form. Another related feature of the same process is what we call furrows. So it's the same idea that the gas erodes it and erodes the channel that you can see here, hopefully, very nicely outlined with the arrows. So here is image of the summer before. Then we had this outblast detected during early spring. And the next summer, we saw this channel coming down to the same point. So kind of obvious that this channel is eroded by this eruption that happened before. Here is another small one, probably from eruption that happened later, and we just didn't get that image in here. Yeah, but they are very similar to the spiders that I was showing in the previous slide, with the difference that they are formed, as you can see, on the crest of the dune. And dune in summer, of course, is a very movable material, so they don't survive. The lifetime of this furrow is 1 year. And we can see the next summer. So actually in 2 Martian years only we got the next image. And the same space is clean. So this was eroded, and then the sand movement was erasing it for the next year or 2. So those are the markings on the actual surface, on the substrate that CO2 jets produced, but we are interested in fan deposits, and I will tell you why in this section, talking about Planet 4 project. So Planet 4, or P4, we call it, it's a citizen science project that we created to study dark deposits from CO2 jets. Why did we want to do that? The motivation behind is that interaction of the Martian atmosphere with its surface is crucial for understanding how the surface is modified. So how those spiders and furrows are created, we can't really know without understanding this interaction with atmosphere. So we also want to know which exact processes are responsible for features that we see. So for example, do those furrows, that's interesting. Are those furrows created from CO2 jets, or are they results of something else? So we want to understand those processes also because they influence what gets preserved in a climate and geological record. So if whenever we want to understand geological record, we need to understand how currently those records are created. We know a lot about it on Earth, But on Mars, of course, things slightly different, and specifically this kind of processes with involving CO2 ice are not happening on Earth. It's too warm here. Also, today's data basically are insufficient to decipher atmospheric influence on these deposits. Basically, we just didn't measure enough about Martian atmosphere to understand how it interacts with the lowest level of the surface. Near surface winds on Mars are specifically very important piece of the puzzle for atmospheric dynamics, for climate change, basically for everything, and we don't know them. We don't have ability to measure them so far. So here is an idea. We could use these CO2 jets because they erupt every spring in polar regions, and we can track via them near surface winds. So imagine that eruption of CO2 jet happens when there is no wind at that time. So the material that the jet brings up will then dynamically, just ballistically, fall out in the atmosphere around the vent. And then you get what's shown here on the top image, what we call blotches. They are kind of deposits around the jets. They are roundish. There is no directionality. That tells you that when that was deposited, there was no wind. And opposite, when there is wind, then while that material is in the atmosphere, it will get deflected by the wind and shaped in kind of fan-like matter. So you get to observe something like this bottom image with very strongly directed deposits. How far the material goes from the vent to the end of this fan tells you how strong the wind is, because of course the stronger the wind, the further away it can blow that material. Also, it can blow the heavier materials further away. So the distribution of the particles from the vent along this fan will be different, and that results in the albedo variation along that line. So we can kind of infer what were the windy conditions when those jets were erupting from the images like this. And we do have a lot of records of these deposits from HiRISE because it's monitored several regions of interest. That's ROI abbreviation for you in this slide. In the Martian polar regions since Martian year 28. So right now it's over 7 consequent Martian years. And HiRISE has a record of seasonal sequences. So basically in one spring, we take several observations, let's say every 2 weeks of the same spot on the surface. Then, of course, there is annual sequences, so covering a Martian year at a time, with not so often as in spring, for example, or fall, but still we do some of the summer observations as well. And then we also have the record of 7 Martian years, so we can compare one year to another. But this is a lot of data to look at. It's a lot of images, and one HiRISE image can have up to thousands of these little, as you can see, about 200 meters long fans. So we needed kind of help with that. That's why we created Planet 4 project, so that citizen scientists, so anybody who is interested on this Earth, can come and help us mark them. So it's currently planet4.space, and if you go there, you can see how this project works. This is showing you an example, and it's currently a little bit updated. So this is the older version. We very recently switched to a new backend for this project. that looks a little bit more up to date and current in the tools that we use. But the idea stays the same. You can see here, if there is a fan in the image, people can use such a ice cream cone tool to mark for us where that fan is located. So this tool gives us start location of the exit vent, basically the length of the fan, the width of the fan, and its orientation, so how it's inclined in the image. If there is something less pointy with less directionality, then people can use what we call blotch tool. So that's actually the ellipse, and it gives us two semi-major axes and orientation as well, and the location in the image, of course. So volunteers are shown such as snapshots, the subframes from high-res images, and they mark for us everything that they see there as the dark deposits. And actually sometimes bright deposits as well, because we don't specify if it should be brighter than background or darker, and sometimes we get the bright fans as well. You can see some of the statistics in here. It's amazing how many people helped us with this, and that we have almost 10 million of classifications to go through now and analyze them. Analyzing those is another big thing, and we had to create specific analysis pipeline that would turn multiple markings from people into the consensus marking of each of the dark deposits. So here is an example of what on top are the subframes of high-res images that people saw. So for example, we're showing them that they mark each of them goes on and marks these dark spots. And then our analysis pipeline that was published last year about Planet for Deposits, you can see the reference on top here. So our pipeline goes on and concentrates multiple markings of each of these objects into consensus what that is shown here in the bottom. So you can think of each of these colorful marking as a result of about 30 markings from different people. So this is already kind of wisdom of the crowd result. And on the right here, I'm showing the fans the same way with the consensus votes that coming from our pipeline underneath here. I will concentrate on this on fans in the following up section, simply because it shows us the wind directed deposits, which are most interesting, so we can figure out wind directions and wind speeds from analyzing these markings. So we can go on now having this consensus vote for each of small markings and consider not a single one of them, but statistically analyze them over the whole high-res image, and then do that for multiple high-res images that we took of the same area. And here is an example of how and what we do with them. What you can see here is the from top to bottom plots progress in time during southern spring. So this is from southern hemisphere, from Elsabes 185 shown here to 227. This is still all spring season. And we plot here histograms. So fun direction histograms are these left plots. And you can see that early in spring, in this region, which called Giza, in Martian year 29, majority of fans were directed towards something like 310 degrees. This is counted from north. So the histogram is very narrow, and that means that basically all the fans that were created were pointing same direction, quite strong prevailing wind during this time. Later, the histogram gets a little bit wider, meaning that either there is new fans that get directed into different locations. Some automatic switch of slides happening here. I don't know why I didn't set that up. Anyway, sorry about that. So the histograms get a little bit wider. That means that there is either more wind directions happening, changeable winds. Maybe there is some other effects in play. But what you also can see that it changes from alphabet to alphabet, meaning the winds actually do turn during this time. On the right-hand side here, histograms of fan lengths. And you can see that that one is kind of opposite. In early spring is a very wide histogram, meaning that there is a lot of different lengths of fans. So probably some of them are shielded by some topography, so they are not so much blown out. Some of them other way around, and you can see also the sizes are quite varying from 20 meters in length to something like 140, 160. Meaning that there is much more variability in the reaction to the wind strength than in reaction to the wind direction. So if we do some assumptions about physics of jet eruptions, we can figure out what wind speeds we are talking about here. With the wind directions, it's straightforward. It's right where these fans are pointing, that's where towards which direction a wind was blowing. So we can directly step from directions to, from fan directions to wind directions, and with some assumptions from fan lengths to wind speeds. And here is what we do. So this is the same information that in the previous plot. Alpha base is now on the x-axis instead of vertical change of plot. Excuse me. And y directions is either wind speeds in meters per second here, or fan directions, or we should call it downwind direction. And you can see how much is changing. So actually the winds rotate through first 40 degrees alpha base, or that would turn into 80 days on Mars from our observations, and then basically turning back. So there is some kind of atmospheric dynamics happening here that changes the wind directions. At the same time, when speeds decrease in the early spring, we see higher wind speeds than in the later part of the season. And now, of course, we would like to compare this to what we currently imagine we know about Martian atmosphere, which is how models predict these things. And there is quite some complexity in how to compare this. This is a different region, and here is the same plot where you can see how the winds rotate, and in this place the wind speeds are actually kind of increasing in spring. And here is a snapshot from a model. So we're using mesoscale model here, which called RAMS, and it's one of the highest resolution, the spatial resolution of the model, and you can see how complex the output of this model is. So here is the wind speeds over this region, basically, which course, this is showing you kind of a map and view from top. You might be used to seeing similar plots from predictions of weather on Earth. So this is the same idea. We see the winds and how they distribute over the area. And this is production at one time, at one LSABS and one site, while from HiRISE and consequently from Planet 4, we don't have such a resolution, especially in time. Each of these points of data that are taken over several days difference, and we don't really know at what point that those eruptions happened, so we cannot tell the precise date to the modeler, basically saying compared to this time of the day during this day in spring. That we just don't have that information. That doesn't work. So we had to invent something how to deal with this. Also, this is the distribution of locations where we could measure with HiRISE. So you see some locations which we are monitoring constantly, so we can make those plots for each of these locations and compare this directly to the atmospheric models. So the atmospheric model had to be run in all these locations and cover the seasons that we cover with HiRISE and Planet 4. So here is the comparison way that we came up with. So you can see here, the LSABS goes now from left to right, and it's in 10 degrees chunks, so 180, 190, 200. The lines, the x-axis here shows you speed, meters per second, and the y-axis is downwind direction, and lines are Planet 4 data. So this is the Planet 4 result for speed in the 180 LSABS bin, and this is the wind speed for the same bin. Sometimes we have couple of images during this bin, so then you can see two lines horizontal, and for example here 3 different estimates for the speeds. The points are from the model, from the mesoscale model, and they are color-coded by daily normalized integrated insolation. So basically how much energy that location got during this period of time. So this is for 1 day. Model is run for 1 day, and all the points are plotted on here. So when we see that our red lines crossing our points, we say that our observations fit to the model. And the best is if this crossing fits, because if it doesn't, for example, how it's shown in this LSABS 210, the wind speeds are kind of coincide with quite some of the points from the model, but wind direction crosses it at different times. So there is no fitting model points that actually cross on the crossing. Model either can fit the wind directions or the wind speeds, but not them simultaneously. So interestingly, you can see on this one, we're hitting it in 2 almost opposite locations during on this diagram during that 1 day. So we did these comparisons for 24 places around the polar cap for 2 Martian years, and from LSABS 170 to 260. I will show you a couple of them. Of course, I can't show you all of what we did. And we also did that for 3 consequent days in the modeling. Of course, model runs, imagine that the model run, and in those alphabet bins, there are 20 days. So which day do you pick to compare to Planet 4 data? So we did try to do that variation. So variation from day to day in models are for several different reasons, but mostly it's a natural variability of, or volatility, what they call, of the lower atmosphere. So here is example from the same plot that before, Manhattan Classic, of 3 different Martian days. You can see that they are similar, but not exactly the same. And you can see that some of them fit in Horizon Planet 4 data better than others. For example, this we would call a good fit, but in this next day, it's not a good fit for the wind speed anymore. So we went through all of this for all our 28 locations. Specifically in this location, if we dig a little deeper and have a look on the topography of where we are measuring these winds and very local kind of background settings, we can see why model probably fails at times. So one of them is that there is a huge chasm with a drop of elevation about over a kilometer from top here to bottom here. So of course, that's a challenge for a model to resolve and to correctly predict the winds here. So the arrows here show you actually our Planet 4 wind directions in Martian year 29 and Martian year 30. You can see that they are kind of repeating from year to year, but they are unusually directed from this point, not towards the deeper channel that we would expect, but kind of across. And that's probably due to what we call the sublimation drag. So basically the surface early in spring is covered by CO2 ice and it's cold. It's a very different situation dynamically to when you have that same surface warmed up by the sun and not having that ice layer. And it can be that one side of this channel gets ice-free earlier than the other side. And that, of course, creates a lot of local turbulence and dynamics in atmosphere that is very hard to pick up for the model. Also in the small scale, which shown in here, you can see all those local, very small slopes that go up and down. So this image would be very, very small part of this topographic mapping here. So we're looking at a smaller scale than this. So this small, tiny scale also can influence how the more global, more upper winds flow over the surface and actually direct the tiny, tiny fans that you can see on this inserted high-res image here. So as I said, we did all this analysis and we publishing it in an upcoming publication, which is basically submitted to the Planetary Science Journal. The only thing that I have left is to upload all this data that we have for 28 locations that we are monitoring. And to give you kind of the conclusion overview for this part is that we observe changes of wind speeds and directions in most of our 28 regions of interest for Planet 4. Surprisingly, Planet 4 observations and mesoscale model are in general agreement. We were happy to see that, but we honestly were surprised because we didn't expect it to be this well-fitting. This agreement is better early in spring and worsens later when the spring progresses and more sublimation flux is happening and more dynamics comes into the low atmosphere. And of course, there are a couple of specific ROIs that present specific challenges. And that's mostly because what I was showing to you, the topography is so greatly varying that it's complicates the dynamics, and basically you need a higher resolution in both models and observations to kind of pin them down. Anybody can get the catalog that Planet 4 produced. It's publicly available for download, and it's connected to that publication of Anya et al. I mentioned before. And overall, this is the first comparison of low atmospheric winds to mesoscale modeling that we are aware of. So we're kind of proud that we could pick that up and do that. And that's all for me. And thank you for listening. I'll take any questions if there are.
Okay, great. Thank you, Anna. Thank you for the nice talk. Questions?
Questions.
Kim, I see you've unmuted yourself. Do you have a question?
No, sorry, I clicked incorrectly.
Okay, no problem.
Now you have to ask a question.
Stefan?
Yes, hi. Very, very interesting. So I imagine these CO2 jets, they're very big. I assume they go on very short timescales.
Great question. And yeah, I did mention that, unfortunately.
Yeah, so basically
yeah.
my follow-up question would be, what would be the feasibility? What would we need to do to like get a live video of such a jet?
We are trying, let's say. So the problem with them is that we don't know exactly when they erupt during the day. We did quite some modeling, and of course there is a lot of assumptions that we don't really know. For example, we don't know if it's really the eruptive and transient event, like you break the ice and everything gushes out and that's it. So that would be tens of seconds, maximum minutes of eruption. That's very hard to catch, you can imagine. If we have the image every 2 weeks to exactly pinpoint that timing is close to impossible. However, we have the other idea that it might be more like outgassing. So you have the conduit with higher pressure, and you have a vent, and you little by little get that gas out. So in that case, we might be more lucky. It's several hours of resource of like what we again can calculate and imagine from all this, like how much CO2 ice can hold the pressure, how much energy is there to actually turn CO2 to gas efficiently during this time. So several hours of outgassing in spring. Probably those jets then not as high as the eruptive event, so they are probably thinner, harder to see. So all these details, every spring we try to catch them in action with HiRISE. We didn't succeed yet. Another reason why might be that it's the gas you cannot see. So if you the only chance for you to image them if that jet is very dusty. So imagine something like Dust Devil on Mars. Probably saw those images. And that's also not very opaque. And as a background, you have mostly CO2 ice, which is quite strongly reflective. So happened to be hard task. We really tried.
Would you advocate to sending a rover in those regions?
Oh yes, but the engineers will not agree to that. It's a tough place to land because it's very rigged terrain, and it's in polar region. That means that there is no solar energy, so you have to bring the nuclear powered one and so on. So yes, we love to, but we know that it's hardly possible.
Okay, thank you.
We're more thinking about high resolution imager that can be in different time of day in the orbit, because like HiRISE is the polar orbit that is locked. So basically it's always images at the same time. And to get different local time, you need to slew to the sides. That means that you're losing the resolution when you look like more inclined to the surface. So what we would like to have is more the images that can change this local time. So we can kind of image at different times to trying to catch that with the high resolution, something like that. That would be our idea of catching them in action. More realistic than actually having a rover.
Okay, cool, thanks.
So I actually have a super naive question, and I might have just missed it. But I think for one of the fans, I actually saw one focal point with two different directional fans. And I was just wondering, like, if there's some expected erasure time, like, could it be like a memory from like many years ago, or like, comment on that?
Very good, both questions are very good, and I want to actually go somewhere faster in there. I want to show you that one of the first one, this one. So you definitely see from one spot there are two fans to different directions. And I don't know precisely this one, but what we often see happening, that early spring is one direction, and later in spring there comes the jet from the same vent, and the wind blows it to the different direction. And that means several interesting things. First of all, that the vent can get sealed and produce second eruption later on, which is on its own interesting how you do that. You have to close that CO2 broken hole somewhat, so redeposit CO2 probably. This also tells you that the wind can dramatically change, be very different. About the memory, there is memories through the season. So what you see here is probably one eruption overlaid by another eruption later on. But from season to season, so more than a year, it's hardly possible to preserve these fans because we see them in contrast with the ice. So the area like in between them, this bright area is CO2 ice with some water actual inclusion. I never mentioned that, but it's very, very minute, so we can just forget about it. So this dark material in contrast to ice is very visible, but when the ice is gone, this material is the same that the surface that is underneath ice in here. So that we lose the contrast, and that's why we cannot observe them like in a year again. So the longer than season record is not preserved in like these visible images, at least.
Oh, great. Thanks. That's good to know. Other quick questions? If not, let's thank Anya again. And I'll clap for everyone.
Thank you.
And have a good day.